Howdy AP PreCal, it's Miss Kosh. We are looking at Mr. Passwater's notes for inverse functions, section 2.8. Unfortunately, I'm tired today, so I struggled through my last video, so we'll see if this one goes any better. And I have not looked at this yet, so I'm just reading straight off of his notes. And ready or not, here we go. An inverse function will undo a given relation. Every inverse relation can be found by switching. That's what I would write, each x and y value. Okay, so when we switch x and y, we get the inverse. In some situations, this process is intuitive, but other times it is not, may not be as obvious. In these cases, it's important that we understand the inverse, as it will help us, I don't know, the nature of inverse relations, the restrictions of inverse relations. I don't know exactly what he's thinking, but that's great. I'm sure it's very good. Let's look at this numerically. We'll look at this numerically with tables, graphically with pictures, and analytically with equations. Okay, so if we have a table and we're asked to find the inverse of this table, we'll switch our x and y's. So what was x becomes y, what was y becomes x. Okay, the original table is a function. Okay, let's see. So each x has exactly, each x maps to a unique y. We didn't repeat any of our x's. The original table is a function because each input, they really like us using the words input and output, has exactly one output. However, the inverse is not a function because we had this input of 2 and 2 that mapped to two different output values. And I'm too lazy to write that, but that's what's happening. That the input value of 2 mapped to two different output values. Okay, sketch the inverse of a graph. Okay, so if I see the point -2, -1, I'm now going to have the point -1, -2. If I see the point -1, 2, I'm now going to have the point 2, -1. Those would be connected. Whoop. Okay, pretend I can draw. Then I see the point, this is 2, 1, so now I have 1, 2. And then I have this is 4, 3, and now I'll end up with 3, 4, which would be up here. And there we go. You'll notice, perhaps, that it has symmetry over the line y equals x. Okay, so an inverse function, or an inverse and its original function, or its original, something and its inverse have symmetry over the line y equals x. Okay, I didn't read his directions, but there we go. Okay, is the original function relation a function? Yes. Is the inverse relation a function? No. Sometimes they'll talk about a function being 1-to-1, where every 1x maps onto 1y, which means that the original is a function and the inverse is a function. They'll use that 1-to-1. This was not 1-to-1. We had like a y value here, where this and this had the same y value. I mean, there were more, but that's one example. The graphs of inverses are reflections over the line y equals x. Super. Okay. Find the inverse, so we could switch x and y, x equals 3y minus 7, add, divide, and there we go. The inverse function is written as f to the -1 of x, or we could sometimes just see f to the -1. Okay, finding inverse with multiple x's. Okay, I don't know, you can pause the video and read all this if you would like to, but let me just jump in and do, these two are going to behave almost identically, so I'll do one and then move on. This is x is equal to y minus 2 over y plus 3. When I can think of cross multiplying. By the way, the domain of this guy is going to be everything except, well, we can't divide. You are not Chuck Norris, you can't divide by 0. Maybe one day Chuck Norris would watch my video. That would be so funny. I'm just kidding. There we go. It took me a minute to write. My brain was doing something else. Okay, so here's the domain and range of this original function. I'm not going to do this one right now. And then when I take its inverse, okay, so one way to think about this is I'm cross-multiplying. I get xy plus 3x equals y minus 2. Ultimately, our goal is to solve for y, so let's get everybody with a y. Nope, you come over, you go away, and you stay over there. Okay, so I have all the y's on one side, all the not y's on the other side, and I can, starts with an F and ends in actor. My students don't think I'm funny either. Okay, so I can factor out a y from those two terms, and then I get y is equal to negative 3x minus 2 over x minus 1. When we look at this, so we would write the inverse function of f. The inverse of f is equal to negative 3x minus 2 over x minus 1. When I look at this, I can tell that my domain goes from negative infinity to 1 because I have an asymptote. We've studied rational functions. Divide the leading coefficients. I know my range is going to be everything except negative 3. And notice what was the domain is now the range. What was the range is now the domain. Super. The next one is just like that, and I don't feel like doing it. Okay. He says, more on graphing inverses. We know that to find an inverse, we simply switch the x and y values. Graphically, this means that the function will be a reflection over the line y equals x. If a graph is not made up of simple line segments, sketching the inverse can be challenging. To do this, we use the fact that a function and its inverse are reflections over the line to help us sketch the inverse. Okay. Sketch the inverse of this. Well, so here's how, I don't know that they're going to make you do this, but here we go. This is the point, what is it, 2, 0, so I need the point 0, 2, which would be here. I see the point 3, 1 and 1, 3. That's not what I said. This is the point 1, 1, so I'm going to keep the point 1, 1, because when I switch 1 and 1, this is the point 3, 1, and so now I need 1, 3, it's up here. And then I see that it's over here, this is 4, this is a nice little quadratic. I see 4, 4, which stays, and I see 4, 0, which becomes 0, 4, and so this lovely little, it's kind of a sideways parabola. Okay, how about I do this one? Well, we're going to keep 0, 0. I don't really want to do this. Okay, this is 1, 0, so now I need 0, 1. I have, yeah, okay. I have negative 2, 0, so now I need 0, negative 2. And then what's going to happen here? Okay, so this is roughly, this is a little bit above 2. So my y value is a little above 2, so now my x value is going to be a little above 2. And it's a little below negative 1, so it's going to be about here-ish. Do you agree with that? And so we're going to have to connect those. And then this one is going to be, it's like positive 1/2, negative 1/2. So now we're going to be negative 1/2, positive 1/2. And so it's going to do, so it's kind of this cubic thing, I don't know, that goes something like that. What do inverses do? If you plug a number into a function, it will generally will output a different number. For example, if we plug this into the function, we get, well, 6 minus, we get 5. Now if we plug that answer to the inverse function, what should happen is we should get back to 2. They will undo a function. So if we plug 2 into a function, plug a number, plug x into the function, then plug the output into the inverse function, we should end up with x again. Okay, I'm just pushing through. We're going to get this whole thing done. Okay, so now this is the algebraic. This is what we need for an algebraic proof. That if two functions are inverses, then f of g of x equals x and g of f of x equals x. This is known as the identity function. If you go watch my notes on composition and inverse, so like the notes that I wrote in my video for that, I talk through this a little bit better in my notes. And I'm not going to do it again right now. To show that two functions are inverses, we must show that the composition of f and g, both, and of g of f, so this and this have to both equal x. I was too lazy to write it out. Okay, so here they've given us two functions. So if I do f, which is 2 times something minus 3, I need of g, so here's the g. This gives me x plus 3 minus 3, which gives me x. Okay, so that showed the first one. Let's do this one over here so that we have space. So now I have g is 1/2 times something plus 3/2. The something is f, so this is 2x minus 3. So this becomes x minus 3/2 plus 3/2, which is x. Okay, sometimes we must use a restricted domain to ensure that two functions are inverses. Okay, so what happens here is this graph is this. if I take its inverse, then I get this, which is not a function. Okay, and so what I have to do, I stand up in the classroom and I use my arms to do this, and I chop off an arm. I mean, I don't really, but I drop an arm. Okay, so what we're going to do is we're going to restrict the domain so that we just have this piece of it, and so then the inverse of that becomes just this piece right here, which is this equation. Okay, and so show that, I think what we would do would be h of k of x, which would be something squared plus 10. This becomes the square root of x minus 10. Technically, when you square and square root something, you get the absolute value of that. But because we've restricted the domain to be bigger than 10, we don't have to worry about that, sort of, is the short answer. The other way would be k of h of x is equal to the square root of x squared plus 10 minus 10, which is equal to the square root of x squared, which is equal to the absolute value of x, but it's x for these purposes. I had a student come ask me, another teacher's student come ask me about this today, but basically the proof here gets a little, like, I don't know that they're going to care that this is technically the absolute value, whereas we say that we need the identity. What I showed her then was that, like, if I graph this and I graph its inverse, so I went to Desmos and I typed in y equals x plus 10, or I didn't, but something similar. And then when I switched, and in Desmos, I typed in x equals y squared plus 10. And that's the nice thing about Desmos versus your calculator, is it doesn't have to be in y equals form. Okay, so what I did is I graphed something, y equals x squared plus 10. It gave me this. Then I turned around and said, okay, well, now give me x is equal to y squared plus 10, which would be the inverse of that. And it gave me this. Okay, I don't know why I drew the axis in one place and not the other, but there we go. And then we talked about how this function is not invertible. But if I call this f of x is equal to x squared plus 10, as soon as I say, what's the inverse function? The inverse function cannot be this. This is not a function. As soon as I use function notation, I can only give you a function. So like this right here would be y is equal to plus or minus square root of x minus 10. But this function can't be this, because this is not a function. If the function notation would just be this, which is implying that we've restricted the domain to just this piece of it, and now we've restricted the domain, so now its inverse is actually a function. Okay, hopefully that clears things up a little bit. So that these below are inverses. I don't think, are they? Oh yeah, they might be. Okay, here we go. So when we have n of p of x would be equal to 6 over, what is this? 6 over something minus 4. The something is 6 over x plus 4. Well, that's gone. So this gives me 6 divided by 6 over x. Well, what would I think of? I would say this is 6 times the reciprocal of this, so this is x over 6, which is just x. I need more space. Let's go the other way. And then that becomes p of, oh, can I finish before kids walk in my door? That was fun. So this is equal to, let's see who walks in first. This is multiplied by the reciprocal, so it's times x minus 4 over 6 plus 4. The 6's cancel. X minus 4 plus 4 equals x. All right, like, subscribe, comment, go practice.